The butterfly effect was the starting point to chaos theory. It required a technical name called sensitive dependence on initial conditions. However, this was not a new notion. For want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of a rider, the battle was lost. For want of a battle, the kingdom was lost. And again, in science as in life, it is well known that a chain of events can have a point of crisis that could magnify small changes. All right, but anyways, we're talking about chaos and in particular chaos theory. So, to begin, the police in the small town of Los Alamos, New Mexico, worried briefly in 1974 about a man seen prowling in the dark night after night, the red glow of his cigarette floating along the back streets. He would place himself there for hours, pacing back and forth, heading nowhere in the starlight that hammers down through the thin air of the messes. The police were not the only ones to wonder. At the National Laboratory, some physicists had learned that their newest colleague was experimenting with 26-hour days, which meant that his waking schedule would slowly roll in and out of phase with theirs. This bordered on strange even for the theoretical division. In the 3 decades since J. Robert Oppenheimer chose this unworldly New Mexico landscape for the atomic bomb project, Los Alamos National Laboratory had spread across an expanse of desolate plateau, bringing particle accelerators and gas lasers and chemical plants, thousands of scientists and administrators and technicians, as well as one of the world's greatest concentrations of supercomputers. Some of the older scientists remembered the wooden buildings rising hastily out of the Remick in the 1940s, but to most of the Los Alamos staff, young men and women in college-style corduroys and work shirts, the first bomb makers were just ghosts. The laboratory's locus of purest thought was the theoretical division known as T division, just as computing was C division and weapons was X division. More than 100 physicists and mathematicians worked in T division. Again, that was the theoretical one, and more than 100 physicists and mathematicians worked in that division. Well paid, and of course free of academic pressures to teach and to publish. These scientists had to experience many things while they were there, and they were very, very, very brilliant, and they were very eccentric. They were hard to surprise. But Mitchell Feigenbaum was an unusual case. He had exactly one published article to his name, and he was working on nothing that seemed to have any particular promise. His hair was ragged, that seemed to have any peculiar sweeping back and forth from his wide brow in the style of busts of German composers. His eyes were sudden and passionate. When he spoke, always rapidly, he intended to drop articles and pronouns in a vaguely Middle European way, even though he was a native of Brooklyn, New York. When he worked obsessively. When he could not work, he walked and thought, day or night, and night was best of all. The 24-hour day seemed too constraining. Nevertheless, his experiment in personal quasi-periodicity came to an end when he decided he could no longer bear waking to the setting sun, as had to happen every few days. At the age of 29, he had already become a savant among the savants, an ad hoc consultant whom scientists would go to see about any especially intractable problem when they could find him. On one evening, he arrived at work just as the director of the laboratory, Harold Agnew, was leaving. Agnew was a powerful figure, one of the original Oppenheimer apprentices. He had flown over Hiroshima on an instrument plane that accompanied the Enola Gay, and then that was to be known as Manhattan, Proctor the Manhattan Project. And of course, he photographed the delivery of the laboratory's first product. I understand you are a smart man, or I understand you are real smart, Agnew said to Feigenbaum. If you are so smart, why do you just solve laser fusion? And even Feigenbaum's friends were wondering whether he was ever going to produce any work of his own, as willing as he was to do impromptu magic with their questions, and he did not seem interested in devoting his own research to any problem that might pay off. He thought about turbulence in liquids and gases. He thought about time. Did it glide smoothly forward or hop discretely like a sequence of cosmic motion picture frames? He thought about the eye's ability to see consistent colors and forms in a universe that physicists knew to be a shifting quantum kaleidoscope. He thought about clouds, watching them from airplane windows, until in 1975 his scientific travel privileges were officially suspended on grounds of overuse. And of course, he would watch the clouds through airplane windows, and then after that, he would watch them from the hiking trails above the laboratory. In the mountain towns of the West, clouds barely resemble the sooty, indeterminate, low-flying hazes that fill the eastern air. At Los Alamos, in the lee of a great volcanic caldera, the clouds spill across the sky in random formation, but also not random. Standing in uniform spikes or rolling in regularly furrowed patterns like brain matter. On a stormy afternoon, when the sky shimmers and trembles with the electricity to come, the clouds stand out from 30 miles away, filtering the light and reflecting it, until the whole sky starts to seem like a spectacle staged as a subtle reproach to physicists. Clouds represented a side of nature that the mainstream of physics had passed by, a side that was at once fuzzy and detailed, structured and unpredictable. Feigenbaum thought about such things quietly and unproductively. To a physicist, creating laser fusion was a legitimate problem. Puzzling out the spin and color and flavor of small particles was a legitimate problem. Dating to the origin of the universe was a legitimate problem. Understanding clouds at that time was a problem for a meteorologist. Like other physicists, Feigenbaum used an understated tough guy vocabulary to rate such problems, such a thing as obvious, he might say, meaning that a result could be understood by any skilled physicist after appropriate contemplation and calculation. Not obvious described work that commanded respect and Nobel Prizes. For the hardest problems, the problems that would not give way without long looks into the universe's bowels, physicists reserved words like deep. In 1974, though few of his colleagues knew it, Feigenbaum was working on a problem that was deep, and it was called chaos. Where chaos begins is where classical science stops. For as long as the world has had physicists inquiring into the laws of nature, it has suffered a special ignorance about disorder in the atmosphere, in the turbulent sea, in the fluctuations of wildlife populations, in the oscillations of the heart and the brain. The irregular side of nature, the discontinuous and erratic side, these have been puzzles to science, or worse, monstrosities. But in the 1970s, a few scientists in the United States and Europe began to find a way through disorder. They were mathematicians, physicists, biologists, chemists, all seeking connections between different kinds of irregularity. Physiologists found a surprising order in the chaos that develops in the human heart, the prime cause of sudden, unexplained death. Ecologists explored the rise and fall of gypsy moth populations. Economists dug out old stock prices and their data and tried to use a new kind of analysis. The insights that emerged led directly to the natural world, the shapes of clouds, the path of lightning, the microscopic intertwining of blood vessels, and the galactic clustering of stars. When Mitchell Feigenbaum began thinking about chaos at Los Alamos, he was one of a handful of scattered scientists, mostly unknown to one another. A mathematician in Berkeley, California, had formed a small group dedicated to creating a new study of dynamical systems. A population biologist at Princeton University was about to publish an impassioned plea that all scientists should look at the surprisingly complex behavior lurking in some simple models. A geometer working for IBM was looking for a new word to describe a family of shapes, jagged, tangled, splintered, twisted, fractured, that he considered an organized principle in nature. A French mathematical physicist had just made the disputations claim that turbulence in fluids might have something to do with a bizarre, infinitely tangled abstraction that he called a strange attractor. A later decade came along, and chaos has become a shorthand name for a fast-growing movement that it reshaped the fabric of the scientific establishment. Of course, chaos conferences and chaos journals abound then as they do today. Government program managers in charge of research money for the military, the Central Intelligence Agency, and the Department of Energy have put ever greater sums into chaos research and subspecial bureaucracies to handle the financing of such things. And as every major university and every major corporate research center, some theorists ally themselves first with chaos and only second with their nominal specialties. At Los Alamos, a Center for Nonlinear Studies was established to coordinate work on chaos and related problems. Similar institutions have appeared on university campuses across the country of the United States. Chaos has created special techniques of using computers and special kinds of graphic images, pictures that capture a fantastic and delicate structure underlying complexity. The new science has spawned its own language in a sense, an elegant shop talk of fractals and bifurcations, intermittencies and periodices, folded tau diffeomorphisms, and smooth noodle maps. These are new elements of motion, just as in traditional physics, quarks and gluons are the new elements of matter. In particle physics, yes, of course. And some physicists, chaos is only a science of process rather than that of state, of becoming rather than that of one of being. Now that science is looking, chaos seems to be everywhere. A rising column of cigarette smoke breaks into wild swirls. A flag snaps back and forth in the wind. A dripping faucet goes from a steady pattern to a random one. Chaos appears in the behavior of the weather, the behavior of an airplane in flight, the behavior of cars clustering on an expressway, behavior of oil flowing in underground pipes. And what about even the behavior of animals and the behavior of humans? Now, no matter what the medium, the behavior obeys the same newly discovered laws. That realization has begun to change the way business executives make decisions about insurance, the way astronomers look at the solar system, the way political theorists talk about the stresses leading to armed conflict. Chaos breaks across the lines that separate scientific disciplines. And because it is a science of the global nature of systems, it has brought together thinkers from different fields and subfields that had been previously widely separated. 15 years ago, science was heading for a crisis of increasing specialization, says a Navy official in charge of scientific financing who was remarking to an audience of mathematicians, biologists, physicists, and medical doctors. Again, that was, quote, 15 years ago, science was heading for a crisis of increasing specialization, end quote. Dramatically, he continues, that specialization has reversed because of chaos, end quote. Chaos poses problems that defy accepted ways of working in science. It makes strong claims about the universal behavior of complexity. The first chaos theorists, the scientists who set the discipline in motion, the pioneers, shared certain sensibilities. They had an eye for pattern, especially pattern that appeared on different scales and at the same time. They had a taste for randomness and complexity, for jagged edges and sudden leaps. Believers in chaos, and they sometimes called themselves believers or converts or evangelists, even in a religious sense, to speculate about determinism and free will, about evolution, about the nature of conscious intelligence, as most philosophical inquiries are known. And of course, they feel that they are turning back a trend in science toward reductionism and the analysis of systems in terms of their constituent parts, quarks, chromosomes, neurons, etc. They believe that they are looking for the whole. The most passionate advocates of the new science go so far as to say that the 20th century science that is continuing on into the 21st century will be remembered for just three things: relativity, quantum mechanics, and chaos. And of course, I've already done a video on the core theory of quantum field dynamics. And of course, chaos, they contend, has become the century's third great revolution in their physical sciences. And like the first two revolutions, chaos cuts away at the tenets of Newton's physics, Newtonian physics. As one physicist put it, quote, relativity eliminated the Newtonian illusion of absolute space and time. Quantum theory eliminated the Newtonian dream of a controllable measurement process. And chaos eliminates the Laplacian fantasy of deterministic predictability. And again, end quote. Of the three, the revolution in chaos applies to the universe we see and touch, to objects at human scale. Everyday experience and real pictures of the world that we see through our sense data have become legitimate targets for inquiry. There has been long a feeling, not always expressed openly, that theoretical physics has strayed far from human intuition about the world. And whether this will prove to be fruitful heresy or just plain heresy, no one knows. But some of those who thought physics might be working its way into a corner now look to chaos as a way out. Within physics itself, the study of chaos emerged from a backwater. The mainstream for most of the 20th century has been particle physics, exploring the building blocks of matter at higher and higher energy, smaller and smaller scales, shorter and shorter times. And out of particle physics and the periodic table that they have masterfully constructed have come theories about the fundamental forces of nature and about the origin of the universe. Yet some young physicists have grown dissatisfied with the direction of the most prestigious of sciences. Progress has begun to seem slow. the naming of new particles futile, the body of theory cluttered. With the coming of chaos, younger scientists believed they were seeing the beginnings of course change for all of physics. The field had been dominated long enough, they felt, by the glittering abstractions of high-energy particles and quantum mechanics. The cosmologist Stephen Hawking, occupant of Newton's chair at Cambridge University, spoke for most of physics when he took stock of his science in 1980, when he lectured with a title called "Is the End in Sight for Theoretical Physics?" End quote. Quote, he said, "We already know the physical laws that govern everything we experience in everyday life. It is a tribute to how far we have come in theoretical physics that it now takes enormous machines and a great deal of money to perform an experiment whose results we cannot predict." End quote. Yet Hawking recognized that understanding nature's laws on the terms of particle physics left unanswered the question of how to apply those laws practically to any but the simplest of systems. Predictability is one thing in a cloud chamber where two particles collide at the end of a race around an accelerator. It is something else altogether in the simplest tub of roiling fluid, or in the Earth's weather, or in the human brain. Hawking and his physics efficiently gathered up a Nobel Prize and several other Nobel Prizes by other scholars and big money for experiments, and this has often been called the revolution. Of course, at times it seemed within reach of that grail of science, the grand unified theory, or the theory of everything, GUT. Physics had traced the development of energy and matter in all but the first eye blink of the universe's history. But was post-war particle physics a revolution, or was it just the fleshing out of the framework laid down by Einstein, Bohr, and the other fathers of relativity and quantum mechanics? Think of Feynman. Certainly the achievements of physics, from the atomic bomb to the transistor, changed the 20th century landscape. Yet if anything, the scope of particle physics seemed to have narrowed. 2 generations had passed since the field produced a new theoretical idea that changed the way non-specialists understand the world. The physics described by Hawking could complete its mission without answering some of the most fundamental questions about nature. How does life begin? Of course, that's for biology, but physics comes from that. Geology and physics comes from, and biology come from the world of physics. And of course, what is turbulence? And above all, in a universe ruled by entropy, when the entropy wins, drawing inexorably toward greater and greater disorder, how does order arise? And at the same time, objects of everyday experience, like fluids and mechanical systems, came to seem so basic and ordinary that physics and physicists had a natural tendency to assume that they were well understood. But this was not so. As the revolution in chaos runs its course, the best physicists find themselves returning without embarrassment to phenomena on a human scale. They study not just galaxies, but clouds. They carry out profitable computer research, not just on Crays, but on Macintoshes. And the premier journals print articles on the strange dynamics of a ball bouncing on a table side by side with articles on quantum physics. The simplest systems are now seen to create extraordinarily difficult problems of predictability, yet order arises spontaneously in those systems, chaos and order together. And so, only a new kind of science could begin to cross the great gulf between knowledge of what one thing does, what one water molecule, what one cell of heart tissue, one neuron of the brain, and what millions of them do. Watch 2 bits of foam flowing side by side at the bottom of a waterfall. What can you guess about how close they were at the top? Nothing. As far as standard physics was concerned, God might just as well have taken all those water molecules under the table and shuffled them personally. Of course, we do not believe in such ridiculous speculations and superstitious ideas. Traditionally, however, when physicists saw complex results, they looked for complex causes. When they saw a random relationship between what goes into a system and what comes out of a system, they assumed that they would have to build randomness into any realistic theory by artificially adding noise or error. The modern study of chaos began with the creeping realization that in the 1960s onwards, that quite simple mathematical equations could model systems every bit as violent as a waterfall. Tiny differences in input could quickly become overwhelming differences in output, a phenomenon given the name sensitive dependence on initial conditions. And again, that's just the butterfly effect. In weather, for example, this translates into what is only half-jokingly known as the butterfly effect. The notion that a butterfly stirring the air today in China, for example, can transform storms or transform storm systems next month in New York. When the explorers of chaos began to think back on the genealogy of their new science, they found many intellectual trails from the past, but one stood out very cogently. for the young physicists and mathematicians leading the revolution, a starting point was the butterfly effect. Richard Feynman once said, quote, "Physicists like to think that all you have to do is say, 'These are the conditions. Now what happens next?'" End quote.